Hello students, today we will study Hydrocarbon Theory Part 2, Section 9.2.1 according to the NCERT. So this is our disclaimer. Now once you have attended this lecture, you will be able to recognize and write structures of isomers of alkanes. Then if I talk about the specific sections of the NCERT, then we will cover the NCERT section 9.2.1, Nomenclature and Isomerism. So we have moved part of it in the previous lecture. We will continue with the remaining part. First of all, we will study about isomerism somewhat, and then we will do some questions upon this nomenclature. So we are starting our discussion on isomers. Isomers are an important concept in chemistry, particularly when studying hydrocarbons. Now let's define isomers. Isomers are two or more compounds that share the same molecular formula. This means that they have the same number and types of atoms. Isomers differ in how their arrangements are arranged. So this can be in terms of their structural arrangement or their spatial orientation, right? Alkanes, which are a type of hydrocarbon, can exhibit structural isomerism. This means that even though they have the same molecular formula, their connectivity of atom can be done in different ways. Let's look at a formula that helps us to find the number of structural isomer for alkane. Now this formula will vary depending on the number of carbon atom in the alkane. So for alkanes with 4 to 7 carbon atoms, the formula to find the number of structural isomer is 2 raised to the power n minus 4 plus 1. Here n represent the number of carbon atoms. Next we have 8 carbon atom in an alkane. So the formula changes slightly. It becomes 2 raised to the power of n minus 4 plus 2. Moving on further, if the alkane is containing 9 carbon, then the formula is 2 raised to the power of n minus 4 plus 3. So this helps us to calculate the number of possible structural isomers. Remember, all these formulas that you have seen just now are used to count the number of structural isomers only. Let us look at an example to make this clearer. We will consider butane, which has the molecular formula C4H10. So this will help us to apply the formula we just learned. In this example, if you see, then it is falling in the region of n is equals to 4 to n is equals to 7. So specifically if I tell, then it is n is equals to 4. Therefore, we will use the formula 2 raised to the power n minus 4 plus 1 to calculate the number of structural isomers. So we put the value of n as 2. So number of isomers is equals to 2 raised to the power 4 minus 4 plus 1, and this will give you the answer as 2. So the total number of structural isomers possible for the formula C4H10 is 2. Moving on further, in isomerism in alkanes. Next, we see that the first 3 alkane are mentioned. So these are methane, ethane and propane. Let's delve into why this particular alkanes are highlighted. Here, we learn that methane, ethane and propane, they do not exhibit isomerism. Okay, so it's important. Only one possible way to arrange their carbon atom is there, and there is no other possible way, and that is the reason they will not exhibit any kind of isomerism. Moving on, we see that higher alkanes starting with those of 4 or more carbon atom can exhibit isomerism. This means they can have different structural arrangements. Alkanes with 4 or more carbon can have multiple structural arrangements. With this higher alkanes, the different structural arrangement can lead to distinct compound known as isomers. So what did you learn in this slide? That first of all, the isomerism is shown by the compound which has at least 4 carbon. Okay, if that is a hydrocarbon, in that case I am telling it should have at least 4 carbon. If it is having 3 or less than 3 carbon, and if it is a hydrocarbon, then it will not show any kind of isomerism, whether you talk about methane, ethane or propane. We have seen that for butane, isomerism is possible. We got 2 isomers for that. Now, in this slide, we are going to explore the concept of isomerism in higher alkanes. Here we have an example of butane, which has the molecular formula C4H10. So we have already seen that butane can exist in two different structural formula, which will be their structural isomers. This means that even though both forms have the same number of carbon and hydrogen atom, they are connected differently. Now we can see two structural isomers of butane. On the left, we have N-butane, where all 4 carbon atoms are arranged in a straight unbranched chain. On the right, we have 2-methylpropane, also known as isobutane, where 3 carbon atoms form a chain and the fourth carbon branches off the middle one. So this different arrangement gives the molecules distinct properties. So you can clearly see that on the second position, we have a methyl substituent. And so its common name is isobutane and its IUPAC name is 2-methylpropane. Let us talk about now chain isomers. So chain isomers are a type of structural isomer where the difference lies in their carbon atom chain. This means that the carbon atoms are connected in a different way, leading to variations in the structure of the molecule. Specifically, butane has two chain isomers. If you see right in the above case, you have two kind of chains possible. First is having a 4-member chain. Second is having a 3-member chain with one carbon as the substituent. So this highlights how even a small molecule like butane can have different form, each with unique characteristics. Understanding these differences is crucial in organic chemistry as it affects how this molecule behave and interact. Now, we will move on to next part. Now we have the example of pentane. So pentane has the molecular formula C5H12. Pentane can form 3 different isomers. This means that the 5 carbon atoms in pentane can be arranged in 3 distinct ways, each resulting in a different structure. You can just calculate this number of 3 by using the formula we saw earlier. Now, we have the 3 structural isomers of pentane. On the left, we have N-pentane. Then, in that case, all 5 carbon atoms are arranged in a straight unbranched chain. On the right, we have 2-methylbutane, also known as isopentane, where 4 carbon atoms form a chain and the 5th carbon branches off the middle one. And the third one, the last one, is 2,2-dimethylpropane, also known as neopentane. So these are the 3 structures, or I would say 3 structural isomers possible for the molecular formula C5H12. Now question arises, what kind of structural isomers are they? So we can clearly say that your pentane can show 3 chain isomers. So the specific type of structural isomerism shown by the alkanes are chain isomers. Now chain isomers differ in the arrangement of the carbon skeleton. So this is a key aspect of isomerism in alkanes, where the carbon chain can be arranged in various ways. If you look on the 3 given structural isomers of pentane, then the first one is having a length of 5 carbon, second one is having a length of 4 carbon, and third one is having a length of 3 carbon, right? As the number of carbon atom increases in the alkane, isomers also increases. So you can you have seen just now that for butane it was 2, now for pentane it is 3. Now here is a question for you. The problem presented here asks us to write the structure of different chain isomers of alkane with the molecular formula C6H14. So let us see the solution. How we'll solve it? In the beginning of the solution, we have to start with the molecular formula C6H14. The next part reveals that the carbon count in the given compound, in the given molecular formula is 6. Here we learn that the number of isomers for this molecular formula is calculated by 2 raised to the power 6 minus 4 plus 1, which will be equals to 5. So this gives us the total number of different structural arrangements possible for this alkane. Remember, here N is lying between the 4 and 7 values. So we will use the first formula. The first structural isomer is shown here, which is a straight chain alkane. It is shown as CH3, CH2, 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 CH3, representing hexane, N-hexane, where all carbon atoms are connected in a single continuous chain. The second isomer is presented as an image here. So this is a different structural arrangement of the same molecular formula, showing a branched chain. Now the image shows us that we have a length of 5 carbon and we have a branching from the left on the second carbon, right? So this is the second kind of arrangement which is possible. Another image appear here. Now you can see that the third isomer is having the same length of the chain. We have just seen that alkanes were able to show only chain isomer, but these two isomers are not the chain isomer because their chain length is same. Now what is the difference between these two? The difference is the position of the substituent. So we can call them as functional isomers, position isomers, because the position of the branching is changing, right? Is it clear? So alkanes can also show position isomer, and this can be seen in your given compound of C6H14, where the 5-member chain is showing 2 substitution, one on the second and the second on the third. Moving on further. Next, what we can say? So next we have the fourth structure of the chain isomer for the molecular formula C6H14, which is CH3, CH, CH, CH3, and 2 substituents are attached here. Now you can clearly say that this is an example of chain isomer because the chain length has decreased by 1 and it is equals to 4. Similarly, we can take one more example. Here the chain length is same, similar to the fourth one, but the position of the substituent is changing. So this is a kind of positional isomer where both the methyl substituents are on the same carbon rather than remaining on 2 adjacent carbon. So this is another distinct arrangement of the carbon and hydrogen atoms, showcasing the versatility of the organic molecule. Each of this isomer can have different physical and chemical properties, even though they share the same molecular formula. Now we see the problem statement asking us to write the IUPAC name for 3 different hydrocarbon compounds. The first compound is a branched alkane with the formula CH3 whole thrice, C CH2, C CH3 whole thrice. The second compound is another branched alkane with the formula CH3 whole twice, C C2H5 whole twice. The third compound is a tetratert butyl methane, which suggests a central methane molecule with 4 tert butyl groups attached. Let us focus on understanding the structure of each compound to determine their IUPAC name. Now, if you see the third question, then it is giving us the name of alkyl chain, and it is a common name, and you have to derive the IUPAC name from this common name. So starting from the first one, here we have an expanded structure of the given condensed formula. So this visual representation helps us to identify the longest carbon chain and any substituents attached to it in a much more convenient way, so that we can determine the IUPAC name for the given compound. Starting with the naming, first we will focus on the word root. The first step is to identify the longest continuous carbon chain in the structure. So this chain will form the base of our compound's name. So we have identified the longest carbon chain in the structure, which is highlighted in the image with a square box. This chain consists of 5 carbon atoms, which is an important detail for determining the word root for compound's name. So we can say that with 5 carbon atoms, so the word root is pent. And since there are no double bonds, so we can call it as pentane. Got it? Moving on further. Next, what we have? Next, we move on to secondary prefix. Now we know what is secondary prefix. It is basically your substituents. Numbering can be done in two ways. In the option number A, we have 2, 2, 4, 4. In the option number B, we have also the same kind of numbering. So either you start from the left or from the right, you will get the same numbering position. Okay. And one more thing you can also say, that on these numbering position where the substituents are present, the substituents are also same. If I take for suppose the option number A, on the second position we have 2-methyl, on the fourth position we have again 2-methyl. Whereas in the option B also, if you consider, if you can count it from the right, then in the option number 2 we have 2 substituents, and in the option number 4 also we have 2 substituents. Therefore, either of the numbering are correct. Next, we can just name the substituents individually. Now, all of these substituents are methyl. You can see here, we have 2 methyls on the second positions and 2 methyl on the fourth position. We will now list the substituents in alphabetic order. So this step is quite irrelevant related to this given compound because all the names are same. Next, what we will do, we will just write the secondary prefix. What it will be? So due to 4 methyl groups, we will use the prefix tetra along with the secondary prefix. This will give us our secondary prefix as 2, 2, 4, 4 dash tetramethyl. So for 4 different substituents, we have 4 different positions, and we have a tetra for 4 methyls. Now it reflects the position as well as number of methyl groups on the carbon chain. We will now move on to the complete nomenclature. What we can say about the complete nomenclature? So for complete nomenclature, we will add the secondary prefix and the word root, which will be 2, 2, 4, 4 dash tetramethyl pentane. So the name fully describes the structure of the compound, including the position of the methyl group and the length of the carbon chain. So we are done with the first compound. Moving on to the second. What is the second one? So if we just expand the second one, which is CH3 whole twice C2H5 whole twice, we will get the given visual representation. Starting with the word root. So what is the longest chain possible here? We can just see here in the given compound, I have squared it. So the longest chain possible here is of 5 length. Therefore, the word root will be pent. And for a single bond, we can take ANE as the suffix. Okay, because there are no double or triple bond present in the given compound. Now moving on further, what we have? We have the secondary prefix. Now, for secondary prefix, first we have to do the numbering. Numbering can be done in two ways. Here you can see that the chain is numbered from left to right. Then it gives us 2 positions. In the case of, if we do it the numbering from the left, we get the substituent on the third position. And in the option number B, we have done the numbering from the right, which is giving us the numbering on the third position. Means both of them are resulting in the same position of the substituent. So we can say that either of them are correct. If we have done this numbering part, now we can move on to the naming of the secondary prefix. You know it very well that these 2 substituents which are present with the pentane ring are methyl, and they are present on the third position. So what we can say, and we don't have to worry about this alphabetic order because it is irrelevant with respect to 2 same names. Hence, 2 methyl are present as substituents. So you can say that the 2 identical groups will be used with di. So di will be the prefix for this secondary prefix. Next, we will get our secondary prefix as 3, 3 dash dimethyl. What we can tell about the complete nomenclature? So for that, we will combine the secondary prefix with the word root. If you do so, you will get your complete name as 3, 3 dash dimethyl pentane. So this was for the second compound. Now moving on to the third compound. So for the third compound, it is given the common name. So for the common name, the structure is given here. So why we are telling it so? You can see here that the common name is tetra-tert-butyl methane. Okay. So we have 4 tert-butyl groups and they are attached onto one carbon because methane is written here. So that is the reason we have joined 3 tert-butyl groups to single carbon. You can see here we have 3 tert-butyl groups. Next, what we can do? Next, we have to identify the longest chain. So this will help us to identify the word root. Now, if you identify the longest carbon chain, you will get this chain as represented here in the given image. Okay. Now the chain is of length 5. Therefore, the word root will be pent, and due to presence of no unsaturation, the ane suffix will be used. So the complete would be pentane. Now moving on further. Next, what we have? Next, we have the secondary prefix. Now for the secondary prefix, two kind of numbering are possible. Again, according to the 1 and 2, you can clearly say that the numbering can be done in the either way because they are resulting in the same position of the substituents. So what we can say that both left and right numbering are equal. Moving on to the next, what we have to do? Now we will just name them. So here we have to use this alphabetical order because all the substituents are not same. So for 4 methyl groups, we will use the word prefix tetra, and for the 2 tert-butyl groups, we will use the prefix di. So finally, we will get your complete name as for the secondary prefix 3,3-ditert-butyl 2,2,4,4 tetramethyl. What will be the complete nomenclature now? You will just add the secondary prefix and the word root. You will get it as 3,3-ditert-butyl 2,2,4,4 tetramethyl pentane. Now next, we will move on to types of carbon atoms. So here we are going to classify carbon atoms based on the number of other carbon atoms they are bonded to. So this classification helps us in describing the molecular structure more precisely. The first type is a primary carbon atom. So this is a carbon atom that is attached to only one other carbon atom. Think it of as a carbon atom at the end of a chain. After that, we have secondary carbon atoms. So these are carbon atoms that are attached to two other carbon atoms. You can imagine them as being in the middle of a chain. Next, we have the tertiary carbon atom. So these are those carbon atoms that are connected to 3 other carbon atoms. So these are often found at branching point in a molecule. Next, we have quaternary or neocarbon atom. So these are bonded to 4 other carbon atoms, making them quite central in the molecular structure. If I try to represent all 4 kinds of carbon atom in the same compound, then you can take this example. You can see here that the first number carbon is 1 degree because it is only attached to one carbon. Whereas the 4th number carbon is 2 degree because it is attached to 2 other carbon. And the 5th carbon is 1 degree. Now, since these 2 carbons are present on the terminal side, so this can be the reason that they have what? They have a 1 degree carbon atom. Now, moving on to the 3 degree carbon atom, you can see for this in the carbon number 3rd. Here, 3 different substituents are attached to the 3rd carbon and they are methyl, ethyl and tert-butyl. So it is 3 degree. If you look on to the 2nd carbon atom, then it is 4 degree. 3 methyl groups are attached onto it and 1 pentyl group is attached to it. So we can say that this compound is having all 4 kinds of carbon atoms. Now we will do the introduction to alkyl groups, so which are very important component in organic chemistry. See that an alkyl group is created when one hydrogen atom is removed from alkane. So this makes our alkyl group useful building block in organic chemistry, as they can be used to form various organic compounds. Here we have the general formula for alkyl groups, which is CnH2n plus 1. This formula indicates that for any number of carbon atom, the number of hydrogen atom will be 2 times the number of carbon atom plus 1. Example, we can have CH3, C2H5, C3H7. So this example show how the general formula applies to specific alkyl groups with different number of carbon atoms. Finally, we see that alkyl group can be attached to longer carbon atom or functional groups like OH. So these attachments can form compounds such as alcohol, which are common in our everyday life. We are now going to learn about the IUPAC naming system. So basically, we are moving from name to structure. So the first step in doing so is identifying the parent alkane from the root name. So this means finding the longest continuous chain of the carbon atom which will serve as the backbone of our structure. Once we have identified the parent alkane, the next step is to draw a straight carbon chain of that length. So this chain represents the main structure of the molecule, and we will build upon it in the following steps. Now we need to number the carbon atom in the chain. So this numbering is crucial because it helps us to determine the exact position of any substituent or branches that may be attached to the main chain. With the carbon atom numbered, we can now place any substituent such as methyl or ethyl group on the correct carbon position as specified in the name. So this step is like adding branches to a tree, ensuring each is in the right spot. So finally, we need to satisfy the valency of each carbon atom by adding appropriate number of hydrogen atom. Carbon typically forms 4 bonds, so we add enough hydrogen to ensure each carbon has a total of 4 bonds. Now, this completes our structure. See, we have a problem here. So we are tasked with writing the structural formula for two specific hydrocarbon. The first compound is 3,4,5 dash tetramethylheptane, and second is 2,5 dash dimethylhexane. So how we'll do it? Remember the steps. So we are starting with a problem where we need to write the structural formula for 2 specific hydrocarbon. The first compound is 3,4,4,5 dash tetramethylheptane, and the second is 2,5 dash dimethylhexane. Let us explore how to approach this. Now we can see the structural formula for the first compound, which is 3,4,4,5 dash tetramethylheptane. So this image will help us to visualize how the carbon atoms and methyl groups are arranged in this molecule. Here we can identify the parent chain of the compound, which is heptane. This means the main chain consists of 7 carbon atoms, and the methyl group is positioned at 3, 4, 4 and 5. So 2 substituents are on the same position, that is position number 4. This fragment provides more detail about the distribution of methyl group. So carbon number 3 has 1 methyl group, carbon number 4 has 2 methyl group, and carbon number 5 has 1 methyl group. This helps us to understand the exact structure of the compound. Now moving on to the next compound. Next we have this 2,5 dash dimethylhexane. So this visual representation helps us to understand how the carbon atoms are arranged and where the methyl groups are attached in the molecule. Here we learn that the parent chain for the compound is hexane, so which will give us a chain length of 6. Next, the methyl group is positioned at 2 and 5. So you can clearly see it in the image that on the second and fifth position we have methyl group present. Next question. We have to write the structure for each of the following compound. Why are the given name incorrect? Write the IUPAC names. The first one is 2-ethyl pentane and the second one is 5-ethyl 3-methylheptane. Now starting with the first one. Now you see that this is the possible structure which is given according to the name, but it is not a correct name. Why? Here, the longest carbon chain that is possible is 6-membered. Okay. And there we have written it as pentane, which is 5-membered. Therefore, the given name is incorrect. So, the longest chain is of 6 carbon atoms and not that of 5. After that, what would be the correct name? So, if you see the structure, you can clearly say that the correct name is 3-methylhexane. This name clearly depicts that we have a 6-member chain, and on the third position, we have a methyl group attached to it. Moving on to the next question. Next, we have this 5-ethyl-3-methylheptane. Now we see an image that likely represents the structure of one of the compound mentioned. So this visual aid will help us to understand the arrangement of carbon and hydrogen atom in the molecule, which is crucial for determining the correct IUPAC name. Here we learn that the numbering and the carbon chain should start from the end that gives the ethyl group the lowest possible number. So this is an important rule in IUPAC naming to ensure consistency and accuracy in identifying the structure of the compound. Therefore, the correct IUPAC name for the complete compound is revealed as 3-ethyl-5-methylheptane. So this correction reflects the proper application of the naming rule, ensuring that the substituents are numbered in a way that gives the lowest possible number to the group attached to the main carbon chain. This was all for today's lecture. Thank you for joining the session. I hope this session was helpful.